it's also affecting things conceptually. And people are now starting to ask questions that you wouldn't really ask before because you didn't have the language to talk about it. And so let me tell you one example from my own research. The standard model of particle physics, the fundamental ingredients involve particles known as quarks. And quarks are the constituents of the proton, but you've never seen a quark in isolation. Quarks carry the strong nuclear force, and the strong nuclear force is itself carried by the gluon. And so quarks and gluons are the fundamental ingredients of the standard model, and yet nothing in our collider data tells us about, oh yes, that's a quark, that's a gluon. It's just coming from an inference process. But with the help of AI, you can actually now study the properties of quarks and gluons kind of independent of the theory, and then separately do a theory comparison. So instead of just having to infer directly onto quarks and gluons, you can kind of have this intermediate stage where you can study quarks and gluons in quotes, but without ever having to make any reference to quantum field theory, and then check what the properties that you've inferred from that does indeed have the bridge that you'd like to the theory land. So it's a way of processing data in a way that can be more agnostic as to the underlying description. Again, I'm still a theoretical physicist. I still want to compare to the theoretical model, but there's a lot more that I can do within the data itself to tease out its structures with the help of AI.
What if, through advancing artificial intelligence, we could gain insights into some of the most fundamental unsolved questions in physics? And what if, through advancing physics, we could unlock new ways to design and scale up superintelligent systems? Well, one person who sits squarely at the intersection of these two questions is Jesse Thaler. He is a physicist at MIT's Center for Theoretical Physics, and he's also the director of the National Science Foundation's Institute for Artificial Intelligence and Fundamental Interactions, or IAIFI for short. I really enjoyed this conversation with Jesse, not just because he's a fun and engaging person to chat with, as you'll soon see, but also because he's one of those few people who's equally comfortable chatting about the big questions like whether the multiverse, as predicted by some interpretation of quantum mechanics, is actually real, and some of the more day-to-day practical ones, like how the research that physicists like himself and others are spearheading could lead to more efficient scaling of large AI systems. With that, join us for this wide-ranging conversation. Let's go. All right, Jesse, welcome to Discovery Engines.
Hey, thanks for having me, Nabil.
Absolutely.
It was great.
Yeah. So when I think about accelerating scientific discovery, physics is one of the areas I'm most excited about. First, because of its practical applications and things like better sensors for navigation or opening up maybe new sources of energy with fusion energy and so forth. But also because of some of the, I would say, larger questions that it touches upon about the origins of the universe, the nature of reality, and so forth. And so one reason I'm really excited to be chatting with you is that you have dedicated your career into really investigating these big questions and their practical applications. And I'm excited to dig into that with you today.
Yeah, great. Looking forward to the conversation.
Great. So let's start off with your CV or your background. So you are a professor of physics here at MIT's Center for Theoretical Physics. You are also the director of the NSF's Institute for Artificial Intelligence and Fundamental Interactions, called IAIFI. You have a PhD in physics from Harvard, a bachelor's of science from Brown in mathematical physics. Did I get that right?
Yeah, that's correct.
Okay, awesome. So maybe just starting off from the beginning, what first sparked your interest in physics?
Yeah, so I didn't know about physics until I was in high school. And like many high school juniors, I experienced physics for the first time. And I always knew that I was interested in mathematics, and I loved the manipulations of mathematical equations. And then to learn that those same manipulations were actually relevant for understanding the physical world was really a revelation. And so in high school, I developed a love for physics. And so when I went to Brown for my undergraduate, I knew that I wanted to study mathematics and physics, but also take advantage of the liberal arts experience at Brown and also take classes in philosophy and history and such. And at the time at Brown, what I realized is that indeed the mathematical structure that I was learning about in my courses had a direct translation to the physical world that you would learn about linear algebra, and really that is the language of quantum mechanics. And I really wanted to dive in deeper. And so when I decided to go for a PhD, I decided I really wanted to work in theoretical physics. I wanted to be using mathematics, but in a way that was tied to reality, as we were discussing. And little did I know that I would be starting a journey that would actually take me outside of the rarefied mathematical realm and actually get me closer and closer and closer to reality as we see it in physics experiments. And so while I'm definitely trained still as a theoretical physicist, I was trained to do pencil and paper calculations, chalk and chalkboard calculations. Increasingly, the work that I do connects to data, and it connects to computing, and it connects to artificial intelligence, which is, of course, one of the great transformational technologies of our time.
Well, very excited to dig into the AI aspect in particular. Maybe before we get there, so the love started with math. You found this really interesting and practical application to reality. What is it about the understanding of reality that piqued your interest or that got you excited?
So I was actually under a misconception when I was younger. I thought that through pure thought, one could figure out how the universe worked. Certainly that's something that we're taught when thinking about some of the great minds in physics, that you would do thought experiments or you would think about mathematical structures, and those would reveal how the universe operated. The reality turns out to be more complicated than that, that you can have the best mathematical understanding of how things work, and that just may not be the way that the universe decides to operate. And so over time, actually, my perception has changed, that it started off by saying, I want to use math to illuminate the way that the universe operates. And now, actually, it's getting revealed information from the universe, from experiments, and then using theory insights to try to infer from that data that you collect in an experiment what really the underlying theoretical description is. But it's changed from me thinking that pure thought was the path forward to really realizing that it's a dialogue between theory and experiment. And you need both. You need the experiments to actually collect the data to see the way that the universe works. But data by itself doesn't actually give you an underlying sense of how things operate. And theory is actually really essential to connect that data to underlying principles, because in many cases those principles aren't directly revealed in the data. You have to infer their presence from the data that you collect combined with theoretical knowledge.
Okay. Well, that's a great then segue into my next question, which is, your profile on your MIT website says you are a theoretical particle physicist who fuses techniques from quantum field theory and machine learning to address outstanding questions in fundamental physics. So for our audience here, maybe who hasn't studied physics, or maybe it's been since that college or high school class, let's maybe break those terms down. So first, starting off with a theoretical particle physicist. What is a theoretical particle physicist?
Right. So I'm a theorist. That means that I dream about the way that the universe could operate, but you don't want to get me anywhere near an experimental apparatus. That said, the work that I do has proposed new types of experiments. The work that I've done has influenced the way that data is analyzed, but the work that I do does not directly involve me, plugging in components, using screwdrivers, anything like that. You don't want me anywhere near an experimental facility. So that's the theoretical side. The particle physics side is that we're trying to understand the fundamental constituents of nature, which to the best of our knowledge to date really consists of particles, point-like objects. And it's kind of remarkable that all the phenomena that we see in nature, at least to date, seems to have a particle-like description. So right now, this table here is illuminated by light, and we think that that light is carried by a photon, which is a type of particle. Even gravity, there's a way to describe at least certain aspects of gravity as interactions of gravitons. And when I started off in my studies, I was hoping that actually this particle perspective would get overturned. And I was studying string theory as an alternative description, that actually these point-like particles, maybe they'd be resolved into these more extended objects. To the best of our knowledge right now, we don't have any evidence for that directly. There's theoretical ideas that push us towards thinking that strings might be more fundamental than particles. But all the experimental evidence that we have right now is pointing in this particle-like direction. And so the study of particles is really studying the fundamental structure of our universe as we perceive it to date.
Well, so then the second part of your description on the website is, mentions quantum field theory in particular, QFT. So how does that relate to what you're describing?
Yeah, so quantum field theory is the mathematical description of particles. And it's really quite remarkable. So quantum field theory does not tell you what particles exist. But they tell you, if I give you a bag of particles, it can describe the interactions of those particles and make predictions. But you do have to put as input what the fundamental particles of the universe are. So quantum field theory itself comes from quantum mechanics, and ideas like entanglement or uncertainty, that comes from quantum mechanics. It has special relativity in there. That's the notion that space and time can transform into each other. You add onto that ideas of locality, that interactions don't happen over long distances, they really happen locally. And you put that all together and out pops quantum field theory. And quantum field theory, once you give me the list of particles in the universe, is an incredibly powerful predictive framework for given a particles, predicting what their implications are. The actual particle content that we know thus far is captured by the standard model of particle physics, maybe not so creatively named, which describes 3 of the 4 fundamental forces and the matter particles that interact with those forces. And again, they all have a particle-like description. And then quantum field theory is the mathematical structure that you use to take those standard model ingredients and then turn them into theoretical predictions.
I see. So maybe staying at that level of complexity for my benefit and for our audiences, follow-up question. So I noticed behind my back here, there is somebody playing a guitar, I think. And, in my, YouTube consumption and book consumption around quantum physics, quantum mechanics, and QFT, one of the things I've heard is, there's this particle wave duality. And maybe this goes back to your string theory work where, in a sense, you could think of these strings as they're plucked in different ways, give rise to different particles. Am I understanding that right, or is that a
that's an overly simplistic view, actually, of what's going on. And the reality is maybe more interesting, but also more abstract. And I'm saying this as a particle physicist, really everything is particles. It just happens to be that if you want to describe interactions of particles and you want to have particles scatter where they interact locally, then you have to package those particles into fields. And these fields are a packaging of a bunch of particles together, and those fields have more wave-like properties. But when you're really looking at the quanta of the universe, they really are particles. It just happens to be that there's a way of also describing them in a wave-like manner. But I'm saying this again as a particle physicist. Other people might flip things around and say that the waves are more fundamental or the fields are more fundamental. But from the particle physicist perspective, there is a way of describing things entirely in terms of particles, of which waves are kind of emergent from that. But it's different than what you were describing in terms of string theory. That's another direction that you might go of trying to understand what those particles themselves might be. But you don't need any kind of string-like perspective to understand this wave-particle duality.
I see. Well, you mentioned this important almost yin and yang between theory and experimental data. And one of the most iconic places for that is at CERN, the Large Hadron Collider. Again, on your website, you talk about your current research is focused on maximizing the discovery potential of the Large Hadron Collider through new theoretical frameworks and novel data analysis techniques. So maybe just starting off for folks unfamiliar with the Large Hadron Collider, the LHC, could you just share more about its history and why it's such an important device?
Yeah, so the Large Hadron Collider is a 27-kilometer ring in Geneva, Switzerland, at a facility called CERN, which is really the focal point for particle physics research in Europe, but really worldwide. And the Large Hadron Collider is kind of a sequence of colliders leading up to it of ever-increasing intensity, that's the rate at which you're colliding particles, but then also increasing energy. And the Large Hadron Collider is the highest energy and the highest luminosity, that's the rate of collisions, collider that we have in current operations. The LHC started taking data in 2010. Famously, it discovered the Higgs boson in 2012, which was really a crowning achievement, the discovery of the last missing particle in the standard model of particle physics. And that's one of the reasons why the LHC is so important. And the subsequent running of the LHC after the Higgs boson discovery has been looking for cracks in the standard model to try to tell whether the interactions that we've already studied in the standard model, whether they might be augmented by additional particles, additional structures. And very carefully on my website, I talk about maximizing the discovery potential of the Large Hadron Collider, because I don't know what nature holds for us. It may be that, to the best of our knowledge and the best of our knowledge 10 years from now, it will just be the standard model of particle physics. Or there could be new physics lurking in the data somewhere, and new data analysis techniques are ways of taking the data from the LHC, processing it in different ways, and hopefully illuminating subtle features that might point us to new phenomena.
Okay. So you mentioned, the scale, the physical scale of the Large Hadron Collider. I went to a talk, actually I believe it was at IAIFI a couple of years ago, where they just talked about the sheer amount of data that comes out of these collisions. And it was in the form of petabytes, which is a word I hadn't even run across before. So, exabytes. Yeah, could you give us a sense of just how much data is generated and how much of it we're able to analyze?
Yeah, so one of the things about particle colliders which makes them different than other types of experiments is that it's a bit like the movie Groundhog's Day, where the same thing happens over and over and over and over and over again. And so every collision at the LHC is set up to be, to the best as we can do, identical. So the identical collision energy, the identical particles coming in, and then what you're looking for is quantum effects that will give you different quantum probabilities for different things happening. So something like production of a Higgs boson, that's very rare. And then there's other types of things that happen which are copiously produced. And we have to make decisions about what data is interesting and what data is less interesting, because the actual data rate at the LHC is mind-bogglingly large, such that even with the best computing infrastructure that we don't have the ability to write all that information to tape. And when I say to tape, I mean literally magnetic tape is actually used as one of the parts of the infrastructure at the LHC. So every 25 nanoseconds, particles collide. 25 nanoseconds. So 25 nanoseconds, that's roughly the amount of time you have to make a decision about whether that event is an interesting collision event that might hold evidence for new phenomena, or it's a boring collision event that might just be a garden variety type of collision at the LHC. And so you might imagine, of course, AI could be very useful if you're trying to make fast decisions. But each individual collision is not so big. Each individual collision roughly is the amount of data that you would have in a kind of 10 megapixel camera image. So each image is not so large. But 40 megahertz, right, or every 25 nanoseconds, that's how much you're coming out. And you have to drop that down from 40 megahertz down to kind of hundreds of kilohertz in order to make it manageable to do for offline analysis. And so it's not an experiment in maybe the traditional way you think of it, an experiment where you get to change knobs and change conditions. Here, the conditions are always the same. The decision making is whether you keep data or you don't keep data. And that's a daunting challenge. And there's always the worry that keeps me up at night about whether we might be throwing out interesting physics because we don't have the right algorithms operating in real time to try to decide what collisions to keep.
So are there, runs that are scheduled over the course of a year, or kind of have the experiments been done, and right now we're sifting through existing data? How is that being approached?
Yeah, so it's a combination. So there is a plan over decades for when you run. So you try not to run during times when electricity costs are high. And there's actually two different modes of running. There's a mode of running where you're slamming together protons, and that's relevant for particle physics, but there's also a mode of running where you're slamming together lead nuclei, and that's relevant for nuclear physics. So roughly 1 month out of the year is spent on lead nuclear collisions. I think it's 8 or 9 months are spent on proton-proton collisions. Then there's time for repairs and things like that. And then there's longer stops that could take a year, 2 years, 3 years sometimes when you're doing major upgrades. But this is a multi-decade project, and there's a lot of negotiation about exactly when you're doing your runtime, because you want to collect as much data as you possibly can. But you should be thinking about continuous. When it's on, it's continuous collisions all the time, every 25 nanoseconds. But you also need to replenish the beam. And so there's a certain amount of running time where you've accelerated the beams up, you have them collide. As the collisions happen, the number of remaining protons decrease. At some point, you dump the beam, restart. So there's a very complicated dance to try to collect as much of data as you possibly can at these colliders.
Well, you mentioned the Higgs boson and the standard model of particle physics. One of the sort of things I've heard anecdotally from physicists is that that model is stubbornly accurate. And as you said, I think we're trying to find cracks within that model. There's also, some other folks who say, well, maybe that's just all that we can get to with this amount of energy that we're able to throw at these particles and to accelerate them with. And so maybe the unlock is going to be in the next generation of particle accelerators. So yeah, could you share more about how you think about that? Clearly, I mean, the benefit of the work that you're doing, and I want to get more into the AI aspect soon, is that the there might be there already, and there's a whole universe of work to be done in order to uncover maybe the signal within the noise. Right. Certainly also seems a lot more cost effective relative to building a big new facility. Yeah. But yeah, how do you think about sort of some of those perspectives on the state of new discovery?
Yeah, so actually it's a complicated thing to negotiate. And in fact, before the Large Hadron Collider, there was a previous accelerator that was actually in the identical tunnel, the Large Electron-Positron Collider. And before it was decommissioned, there was actually potential evidence for the Higgs boson lurking in that data. And it was an incredibly challenging decision to say, you know what, we're going to decommission that particular accelerator and build a higher energy collider, the Large Hadron Collider. And once you gutted the tunnel, you couldn't go back. And so that's a complicated negotiation to say, should we continue to collect data at the current machine? Or do you actually go and build a higher energy or a higher luminosity machine to try to get a different type of data? And that is what our field is wrestling with right now, or has been wrestling with. And we've made collectively a decision that we are going to launch the high luminosity upgrade of the Large Hadron Collider. And that upgrade had a very particular target in mind, that given all the various technologies available, one of the things that we'd really like to understand is understand a particular property of the Higgs boson, which I'll describe in a moment. And it was decided as a community that the best way to get access to that information was indeed to run the LHC, but in this higher luminosity mode, collect more data, roughly spend another decade collecting data, and that would be the best chance for us to understand this particular property of the Higgs boson. But it's a complicated decision, because when you're doing that, that means that you can't do something else. And so again, it's a collective decision of the community through a lot of strategic planning to make that decision. But the reason why this particular property of the Higgs boson was so important was that we know that the Higgs boson is responsible for giving elementary particles their mass. And the degree to which the Higgs boson talks to various particles, that's proportional to how much mass they have. So the heaviest particle in the standard model is the top quark, and the top quark also has the strongest interactions with the Higgs. And we've measured the interactions of the Higgs boson with top quarks, with W bosons, Z bosons, but we've never measured the interaction of the Higgs boson with itself, because the Higgs boson itself has mass, and therefore the Higgs should in some sense give itself mass. And that was the scientific target that was used to decide basically how much running to do. And there's other science you can do besides that really big ticket item, but that was the thing that drove the decision for roughly the next decade of having running in this mode of continuing the LHC. And now the decision is, well, what do we do after the LHC? What's the next collider that we build? And we're part of a strategic planning exercise. There's a version of it that happened in the United States that's called the SNOMAS process. And I served on the panel called the Particle Physics Project Prioritization Panel that made recommendations to the US government about how to prioritize activities in the US side of particle physics. Now there's a European strategy group that's meeting to try to decide things on the European side. And they are deciding, in some sense, what is the next accelerator that you would build after the LHC. And we're having these conversations of the trade-offs of different technologies, different timeframes, what is the science that we want to uncover. And those are really fun conversations to be had. And hopefully we'll come to a community consensus about what the best path forward is.
Well, one thing that I find so, I would say, heartwarming, and I'm sure it's different maybe when you're actually at those conversations, but from the outside, when I think about just grand projects that we take across nations, today, the LHC really stands out as one that is, financed, as I understand it, for multiple nations, involves scientists from all over the world, and by virtue of the fact that you can only create one of these or so many of these, you need to engage in this collective decision making with real tangible outputs and impacts on science and so forth. So I guess what can we learn from that process that from the outside seems like an inspired one?
Well, the particle physicists have had to do this out of necessity. Not everyone can have their own accelerator. There was a time when everyone really could have their own accelerator, and different universities would have their own private accelerator complex. But as you're going to higher collision energies and higher collision rates, you end up getting it to be cost prohibitive. And so the community, out of necessity, had to work collectively. And examples where we didn't work as collectively and where we maybe didn't get consensus of the community as a whole, those have been situations where particle physics hasn't done as well. And we've done our best science and engaged, the most science has also engaged society at large most effectively when we've done these big community efforts where there are multiple different science outcomes that come from the same machine. And so the LHC is not really just one experiment. It's many, many, many different PhD theses that are generated from the LHC. And so you're really trying to build an apparatus that can serve a huge range of needs of the whole community. In terms of the lessons that we can learn elsewhere, is that really in this era of big data and big science, which seems to be necessary to push the frontiers of knowledge, you really do need to have that community thinking. And the conversations that are happening now in the world of AI are ones that also drive us in that direction, that if we really want to see, coming from the academic side, great advances happening in AI, we may also need to do that kind of collective action and think about building AI models that are actually community efforts as opposed to small author list work, which is more typical in this area. But particle physics offers a very interesting case of, out of necessity, having people get on the same page and make collective decisions.
Well, I think there's really more than one interesting connection between physics and AI, and in the way in which both, you could say communities, and in some cases there's, it's the same folks who are physicists who are working at these AI companies are trained up through physics and then able to contribute, contribute to the AI, and the AI contributes to the physics. So going to, the other hat that you wear as director of the Institute for Artificial Intelligence and Fundamental Interactions.
And I'll use this opportunity to take a sip from the mug so you can see the
There
IAIFI
we
logo
go.
here.
Could you share more about the origin story of this organization and what its mission is?
This actually goes back to 2016, when a number of my friends were using AI or starting to use AI for particle physics applications. So around that time, you were seeing incredible advances in computer vision. And so particle physicists were taking advantage of that to try to apply it to data analysis tasks at the LHC. And in 2016, I'm on the record as making the following joke, all the stuff going on in the world of deep learning, why are my theory friends doing this? We're in the business of deep thinking. And that was a joke that I made in 2016, quite dismissive of what was happening in the AI world. And if I'm really honest with myself, it was really that I was feeling threatened because a lot of the theoretical work that I was doing was being supplanted by AI advances, such that I was developing new data analysis techniques. But AI was in some sense developing its own techniques that were direct competition with my work. And indeed, my work is often used as a punching bag for AI benchmarks, where you say, how much can you beat Jesse's strategy? So that's what was going on in 2016. And at that time, that fall, two graduate students, Eric Metodiev and Patrick Kamitsky, came into my office. They were new graduate students, really excited about using AI and applying it to physics. And I was quite dismissive of the work that they were doing. And I was telling them all the things about their research program that didn't make sense from my theoretical perspective. And I thought I'd never see them again. I was kind of, get off my lawn, curmudgeon style. But they actually continued to do their PhD work with me, and they showed me the way that AI gives us new perspectives on problems in particle physics. And now there are things that I can't unsee. That is, the way that machine learning and AI gives you a different lens on your problems are ones where I really see that as the future of how we do scientific investigations. So that started in 2016. I went on sabbatical, and that sabbatical a few years later really cemented my excitement about AI, and then coming back from sabbatical, there was a call from the National Science Foundation to launch new AI institutes. And so folks at MIT, along with Harvard, Northeastern, and Tufts universities, we got together and put in a proposal that ultimately was funded with me as the director of this institute. And that joke that I had before about deep learning and deep thinking, the tagline of IAIFI now is deep learning plus deep thinking equals a deeper understanding. Both a deeper understanding of physical systems, but also a deeper understanding of how AI itself works. And so people know, at least have some conception of what deep learning is. This is this AI revolution. Deep thinking are all the things that I learned as a student in physics, the way that you analyze complex systems, break them down into the fundamental pieces, things like symmetries that we teach all MIT students about in their classes. And you take those physics insights, you combine them with the AI revolution, and indeed we have seen a deeper understanding coming out of our institute. But it started off with me being very suspicious about AI and dismissive, honestly. And then my perspective transformed, and now I'm very much an evangelist for this toolbox of advances from mathematics, statistics, and computer science, kind of under this broad umbrella of AI, and what the potential of that is for scientific advancement.
Well, in a way, spoken like a true scientist. When given some data that opposed your viewpoint, you then updated accordingly. Okay. So I want to get into both of those parts, what AI is doing for physics and what physics is doing for AI. So maybe just starting with the first one, could you describe some interesting breakthrough or just novel approach that you've seen where AI has really been leveraged to maybe help with looking through and sifting through that data from the LHC or other experiments?
Right. So we talked before about this synergy between experimental work and theoretical work. And the bridge between experiment and theory is known as inference. So inference is a process of given data to try to, as best as you can, figure out what the underlying theoretical description is. And what AI has done is allowed us to do much more sophisticated inference techniques that can take maximal benefit from the data that we've collected and apply it in much more sophisticated ways to theory. And so when I was a graduate student, what you would see is you would see plots coming out of colliders. Despite the fact that you have this massive amount of data, all the data was kind of compressed onto a histogram. One dimension, you make some plot, you see some bump, you declare victory. But one dimension, this massive high-dimensional data set being projected down just to one dimension. With AI, you can really work with that entire high-dimensional feature space, all the intricate information from that collision debris, and use that to do inference. And so, whether you would call it machine learning or AI at the time, certainly the discovery of the Higgs boson was aided by various AI-style techniques, and arguably we discovered the Higgs boson faster than people thought because you were taking advantage of AI's ability to find those complicated patterns. But now, more recently, you're now seeing heroic analyses where you can do this theory-experiment comparison in ways that are way more sophisticated because you have this ability to, well, even though we as humans can't visualize that high-dimensional spaces, the AI can, and it can make decisions about what is or is not most likely in the universe based on this full high-dimensional space. So that's one of the ways that the AI, in a very concrete way, is affecting particle physics. But it's also affecting things conceptually. And people are now starting to ask questions that you wouldn't really ask before because you didn't have the language to talk about it. And so let me tell you one example from my own research. The standard model of particle physics, the fundamental ingredients involve particles known as quarks. And quarks are the constituents of the proton, but you've never seen a quark in isolation. Quarks carry the strong nuclear force, and the strong nuclear force is itself carried by the gluon. And so quarks and gluons are the fundamental ingredients of the standard model, and yet nothing in our collider data tells us about, oh yes, that's a quark, that's a gluon. It's just coming from an inference process. But with the help of AI, you can actually now study the properties of quarks and gluons kind of independent of the theory, and then separately do a theory comparison. So instead of just having to infer directly onto quarks and gluons, you can kind of have this intermediate stage where you can study quarks and gluons in quotes, but without ever having to make any reference to quantum field theory, and then check what the properties that you've inferred from that does indeed have the bridge that you'd like to the theory land. So it's a way of processing data in a way that can be more agnostic as to the underlying description. Again, I'm still a theoretical physicist. I still want to compare to the theoretical model, but there's a lot more that I can do within the data itself to tease out its structures with the help of AI.
In a previous episode of this podcast, I interviewed an investigator at the ARC Institute. It's a funded organization that does really interesting work in building foundation models for biology. And they build the self-proclaimed largest ever model in biology, EVO2, released it a couple of months ago. And in talking with them, they had a partnership with NVIDIA. Also, Greg Brockman, co-founder of OpenAI, helped out with the team. And one of the things that I learned is, in getting this model to be developed and to work, there was almost just as much effort in the structural engineering of being able to, for example, take this many GPUs and make them work together to be able to do training on these models in order for them to, be able to break down a model into its component parts and still train it as a whole model. And having OpenAI's, for example, expertise in that was really valuable to the ARC Institute. I'm wondering, as you've seen the application of AI for physics, you talked about, the petabytes, exabytes of data coming out of the LHC, needing to put that onto magnetic tape just because of the volume of data. How much of the challenge is around, coming up with interesting new algorithms that are more useful and clever versus just the engineering of, building the right, size, cloud computation facility in order to make this work happen?
Right. So there's kind of two different aspects of it. One aspect of it is indeed the infrastructure aspect. But in particle physics, where we're operating is so far different than what's happening in the more commercial realm that we are leading the way in developing the AI toolbox because we need things that are faster and more robust than anything that's really needed in an industry context. So there's an effort in fast machine learning where you're trying to make a machine learning that can operate at this trigger decision level at the LHC to try to decide whether or not to keep events. And that's something where we are at the forefront, that we are developing techniques that are now applicable elsewhere. The other aspect, which is I think we don't really know which way it's going to go, is this, in some sense, the tension between deep learning and deep thinking. That there is certainly advances that are happening by just throwing a lot of GPUs at the problem. And I'm always shocked how much how well things scale by just putting more compute at the problem, more data at the problem, how things improve. But there's also like the deep thinking part, that embedding your physics knowledge into the AI. And that's an interesting type of trade-off, because if you're doing things on the more compute end of the spectrum, yes, you can benefit from industry advances. If you're building custom AI tools that have physics knowledge built in, that's harder to benefit from industry advances, but then you are kind of guaranteed that you have the physics knowledge in your AI architecture. And I think that's where it becomes a very interesting trade-off. And I think we're still deciding to what extent is domain knowledge relevant or not. It probably really will depend ultimately on the quality and availability of the data to see which kind of technique wins out. But a lot of the work that I do, it even runs on laptops. You don't actually need super fancy, big GPU infrastructure. And yet it's still impactful. And that's an interesting thing that happens when you actually do bake in physics knowledge, that oftentimes you can have the training be more efficient than you would if you didn't have that physics knowledge to begin with.
Well, I think that's really exciting. Also, just from, I went to the Sloan School here at MIT and always thinking through things on the business end of things. And as you are, in a way, from one of the things we talk about is extreme users in different areas. As you're an extreme user of data and sensors and so forth, some of the breakthroughs that you need to have in order to be able to do your work, I imagine have really interesting applications, whether they're top of mind right now or going to be top of mind in the next few years, right? You talk about making quick decisions. Well, I think about, robotics that have embedded AI systems that themselves need to make quick decisions with data that comes in. What parallels are there? So yeah, how do you think about that?
The work that I do is curiosity driven. And I certainly am not doing my research with an idea about how it might be used elsewhere. But it is pretty remarkable how techniques that you develop with a particular physics context in mind end up being relevant in other applications. And one way of thinking about it is that for us, we have to develop a technology. Otherwise, what we do doesn't work at all. Whereas in other contexts, there's a trade-off, and there may be multiple technologies that you're deciding between. But if someone gave you as a gift something coming from the curiosity-driven realm and said, hey, here's this new technique, then of course you would adopt it. And that's what we've seen with various technologies that have been developed in particle physics, independent of AI. And now we're starting to see it more with AI, in particular with fast machine learning, where fast machine learning is relevant to a variety of disciplines, obviously not just in physics. Now, we happen to have the most extreme needs on time, but you can scale those things back and of course is relevant but beyond there. And it ends up being an interesting question. If you knew ahead of time that your goal was to develop that technology, would you nevertheless still want to fund the curiosity-driven research to make that happen? And I don't know the answer, but I am always amazed about some of the practical applications of the work that we do in physics that can be quite different from what our intended original application was.
Mm-hmm. Well, in chatting with folks who have chatted themselves or worked at some of the big labs, a la Anthropic and OpenAI and so forth, I think one of the things that they really value in the perspective that physicists bring to their teams is, one, they often don't trust the data, and they're very good, very good at taking that first level of analysis. I think the second is there's so much emphasis now on interpretability or explainability of these black box models. Yeah. And for me, the analogy of the data that's coming out of a collision, where you're trying to understand the multidimensionality of it and create kind of frameworks and models that might map onto the real world. That seems to be an obvious parallel. A third that I've heard about is just the interesting parallels and maybe inspiration from diffusion in thermodynamics that then has been the backbone of a lot of these image generation and video generation models that are kind of all the rage these days. So to me, some of those kind of the way in which physics is now informing AI, there's already evidence of that, which I think is really exciting. But
I mean, diffusion models are a really great example of why is it that a physical process that in some sense scrambles information, why should that be really good at generating images? And of course, it's not actually diffusion in the forward direction, it's actually reverse diffusion is what we're using to generate images. And there's been work at our AI Institute of trying to understand more generally what types of physical processes are good for generating images more generally. And it turns out that, for example, some of the equations that we teach our first-year students in electricity and magnetism, some of those equations are also very good at generating images, which may not be so obvious. But there definitely is this interesting perspective that physicists bring to problems. And one aspect of it is that we need to understand both why something works, but we also need to understand ways that we can break it. And when you're doing empirical studies, a lot of the studies of AI are being driven by just doing experiments, not experiments in the physics sense, but experiments in the AI sense. And physicists are very good at exploring the whole space of possibilities to make sure you understand when things do work, when things don't work. And instead of being content with seeing one example and trying to draw a conclusion from that one example, physicists often want to explore, because we have experience with physical systems, that physical systems often exhibit exotic phases. And so just like water can be in liquid form or in ice form as solid or gaseous form as vapor, we also have evidence that AI systems also exhibit different types of phases. And that's something that physicists is very natural to think about in that language. And so that's really good to explore kind of different behaviors of AI systems by thinking about them almost like physical systems that you can poke and prod.
So there's a lot of investment being done right now in AI on the commercial end. In academia itself, at MIT, we've got this new Schwarzman Institute of Computing, and at CSAIL and so forth. As you look out into the next 5-10 years in the way in which AI can help advance physics, what are you most excited about?
Yeah, so I had a transition, as I mentioned, when I saw that AI could influence data analysis, and that transition happened from 2016 to 2020. and 2020 is when our AI Institute launched. 2 years later, you had ChatGPT come out. And again, I found myself in this more curmudgeon-y mode of saying, oh, what are these large language models? I would ask ChatGPT at the time questions about particle physics, which it gave beautiful but hallucinated, incorrect answers to. And that's something that I've also started to change my mind about, and change my mind about in two ways. One is realizing that data is more than just numbers or equations, that also text is a type of data. And realizing that a lot of what we do already in particle physics is we write papers and emails and such to each other. Like, that's how we communicate. And realizing that that's actually a very rich way of communication. And so now as you're starting to see these large language models evolve to really become reasoning engines or even kind of agentic AI, you're starting to see this capability for interacting with humans in a new way. And you're hearing people talk about wanting to build an AI physicist as a type of a digital collaborator. And this is something that doesn't seem so far-fetched to me. And it may be that in the next 5 to 10 years, indeed, you will be, right now, I couldn't live without Mathematica, which is a program for symbolic manipulation. And it may be that in 5 to 10 years, I won't be able to live without a system that can do kind of conceptual manipulation with me. And that seems more on the horizon now than I might have anticipated back in 2022. So that's one thing that I'm hoping for over the next 5 to 10 years. The other thing that I'm really hoping for in the next 5 to 10 years is that physicists will help come up with a way of breaking through some of these scaling behaviors that we're seeing with AI systems. So it is known that if you take an AI system and you make it bigger and bigger and bigger and you add more and more data, that it gets better performance. But it doesn't get better performance in a way that's linear with the amount of resources you're throwing at it. It only grows slower, it grows logarithmically. And okay, for commercial applications, maybe you can throw that type of money at the problem. But if you're trying to do curiosity-driven research, we really can't afford to do that type of scaling. And so my hope is that someone from the physics community or for the science community more broadly might come up with ways to actually have more favorable scaling. That is, you're putting more resources in, you get comparably more output coming out. And there's an interesting historical example of this that happened in particle physics when you had a transition in technology from old style accelerators to new style colliders, where you had a change in the technology that changed the scaling behavior. So accelerators, you pay a certain amount of money to get beams to a certain energy. And what you would do with those beams is you basically throw them into a brick wall. And the total amount of effective energy that you get, if you put a certain amount of energy in, you only get a square root of that energy out in terms of the effective collision energy. And so the technology of the collider allowed you to take the full energy that you're putting in by having colliding beams so that the full energy is going into the collision process. And that change in technology, that change in scaling behavior led to a similar change in our ability to make discoveries. And so one would hope that maybe we can come up with AI systems that have more favorable scaling behaviors, such that as you're putting more resources to it, you actually get more out, and it may be that physicists could have the best background for maybe coming up with that new type of scaling behavior that could actually make AI even more powerful than it is right now for the same amount of resources.
Wow. So real impacts to being able to push physics forward, but also just to, as we think about the incredible infrastructure needs that we need to build out nationally in terms of energy and storage and so forth, reducing the needs for that or being able to get more bang for a buck.
That would be incredible, and with broad applications, yes.
Yeah.
So that's something that I'm hoping for might happen in the coming decade.
Okay. Well, I, as a science nerd and a burgeoning physics or a nascent physics nerd, have read some books on popular physics and interpretations and so forth. So there's a few theories that I wanted to throw at you in a quick popcorn style and just get your quick take on them. Okay. All right. Yeah. So Einstein, in a 1955 letter of condolence to the family of his lifelong friend, Michael Besso, wrote, "The distinction between past, present, and future is only a stubbornly persistent illusion." Quick take.
So something that does seem to be fundamental is causality. While time itself is something that can be manipulated and twisted around, it does seem like, yes, the past does influence the future and not the other way around. But indeed, when you look at the equations of fundamental physics, time is this malleable thing. And while causality seems to be preserved, exactly the notion of time orderings is something that is indeed flexible, as Einstein said.
Donald Hoffman, professor of cognitive science at UC Irvine, he wrote a book that I read a few years ago. He talks about the essentially interface theory of perception, this idea that through evolution, we essentially solve not for being able to see the world well, but being able to survive. And so ultimately he talks about reality being this interface. And he says famously, space-time is doomed. It's not real. It's an interface that we impose on reality. Yeah. Thoughts on that?
Yeah, so quantum field theory, the mathematical framework that I work on, really takes space-time as the tapestry on which everything happens. But we know that eventually, if you get enough or extreme enough gravity, that indeed the structures of quantum field theory start to break down. And while there is a notion of quantum gravity that works for a while, you can talk about gravity in terms of gravitons for a little while, eventually you get a black hole, or eventually you get the Big Bang start of the universe, and the notion of space-time completely collapses. And so indeed, the fundamental description of the universe will probably have space-time as being an emergent property. But for the work that I'm doing at the LHC, space-time is the tapestry on which everything else is painted.
Awesome. So in popular fiction, and it's almost become sort of, slang, talking about, I'm glad that I'm in, or I'm not glad that I'm in, this, what's it called, like branch of the universe, or this reality, right? It's become a meme in a lot of cartoons. Yeah. When I dig into that, there's essentially a lot of it has to do with quantum mechanics. There's a Copenhagen interpretation of quantum mechanics, which states that, upon measurement of an observer, a wave function collapses into a single definite state. I think Hugh Everett's theory of the universal wave function says that each branch of this superposition is equally real, and we exist within each of them. Your take, Jesse.
So maybe just to say where this is coming from, the challenging thing about quantum systems is that you also have to take into account the quantumness of the observer. And you can't separate you yourself as an observer from the quantum system that you're trying to study. And this makes it really complicated to describe. One way of describing it is with the collapse of the wave function. The other way of describing it is with the many worlds interpretation. Mathematically, you get the same answer. But I would say that philosophically, what I like about the many worlds perspective is that it preserves the notion of probability. And I'm not sure that I would say that each branch of the universe has the same notion of reality, but it has certainly a notion of probability in the same way that if your favorite sports team loses, there was a branch of probability in which they won the game. There was some betting odds that they won. Yes, that's maybe not the universe that you're occupying, but it's not as if the fact that you observed the system to be in one state doesn't mean that there wasn't a reality or the possibility that your team might win. And similarly, the fact that you've observed something doesn't change the fact that there really was a quantum probability for you to have seen something else. And in that sense, I like the Everettian type of approach to things, because it preserves that notion of probability, and probability seems to be kind of fundamental to the description of the universe.
Okay. So if your favorite sports team did lose, you can't necessarily take solace in the fact that they are winning in a different universe. They might just have lost.
They might just have lost, and yet you might have been perfectly justified in placing your money on that team. Yes. Yeah.
Great. Last one, which relates to our conversation in AI. Demis Hassabis, the founder of DeepMind, on his Twitter, I believe since last time I checked, he says, seeking to understand the fundamental nature of reality or of the universe. And he's also said, if we solve intelligence, then we can use that intelligence to solve everything else. And by everything else, he means a lot of deep scientific questions. Clearly, he's been all in on this. But yeah, your perspective on that.
Yeah. So first of all, it's an incredible idea. That if you could take aspects of human intelligence and really scale it up with computers, you think about what human minds have been able to do over the centuries, and really have that kind of amazing growth if we can scale it up. I think my perspective is one, the challenges that we're facing are probably ones where intelligence alone is not going to be enough, or at least human intelligence style alone will not be enough. And actually, one of the things that computers are able to do is allow us to transcend beyond human intelligence and even come up with new types of intelligence, or at least new ways of processing or parsing data. So while it's very seductive to think that, oh, all I need to do is build an intelligent system in the human style of intelligence and unleash it, actually, my sense is that we're going to see that there's multiple different types of intelligence good for different types of problems. And there are probably still problems for which brute force search with the computer algorithm, that might be the best path forward, and that the kind of human intuition may not actually be relevant for all scientific problems. And so more generally, I'm enthusiastic about computing mathematics statistics as an engine that drives things, of which intelligence apparently seems to be subsumed under that umbrella, remarkably to me, under the banner of AI. But it may be that even more traditional computational strategies will be equally important, and we should not seek intelligence by itself without also pushing on the frontiers of computing more generally.
Once again, we get to that yin and the yang.
Yin and the yang, yes, that's right.
Fascinating. Yeah. Great. Well, Jesse, for folks who want to help, contribute, partner with IAIFI or the work that you're doing here at MIT or any of your other projects, what's the best way for them to help out?
Oh, so you can of course go to ifi.org and find about the work that we're doing. But I guess there's three things that I would ask of your viewers. So one is that if you're in a position to advocate for curiosity-driven research, please do so. That the type of research that we're doing, this more fundamental research, we don't always know where it's going, but at least historically we've seen that it's had transformational impact. And AI plus physics seems to be this new area that, with support from foundations, support from the federal government, support from private individuals, can really blossom. And I think that curiosity-driven research is a really powerful engine going forward. The second is that if you're in a position to hire people working at this intersection of AI plus physics, they're incredibly talented. They see the world through this multifaceted way. And even if your problem doesn't seem to be one that's physics specific, if it involves a type of data analysis or just deep thinking about the way that a problem could be solved, then the people who are coming out of our AI Institute or more generally in AI plus physics, please hire them because they're spectacularly talented. Hire them, of course, in academic circles, in national lab circles, and also in industry contexts. And then the last thing that I would say, this is something that I heard at an MIT education forum, is please don't be an ostrich. AI is quite scary in terms of its way to transform society. It's also quite exciting, but don't sit on the sidelines. Don't pretend like it's going to go away, and engage with it in whatever way makes sense to you. If you haven't actually played around with one of these large language models, spend some time working with it. Try to understand what it can or it cannot do. But definitely don't ignore it because it's poised to change scientific research, it's poised to change education, it's poised to change society. And the more you can learn about that, the more informed you are about its capabilities, the more that you as a citizen can make informed decisions about what things to support or not.
Well, thank you for that. Jesse, just personally, I've really enjoyed this conversation, and I just really appreciate the work you're doing both on the practical end of developing, the U.S. workforce and our next generation of AI specialists and physics specialists, to also helping just advance humanity's knowledge of some of these large questions that I think sparked our interest back in that high school science class, and that we want to see continue to evolve and make sense of. So really appreciate your efforts in this conversation.
Oh, thank you so much, Nabil. And thanks to all of your listeners and viewers as well. Hopefully they found what I talked about to be interesting, and hopefully they'll find ways to incorporate AI into whatever they're doing in their lives.
Okay, thank you so much.
Thanks so much.
All right. Well, thank you for joining this episode of Discovery Engines. I'll link below in this podcast episode links to IAIFI and MIT Center for Theoretical Physics. If you want to get more updates, join our newsletter at discoveryengines.co. Thank you.